Everybody, welcome back to the section 2.5 video. In this video, we're going to look at another example of solving a Bernoulli equation. Okay, but this time we're going to take a look at an initial value problem. So where we're giving an initial condition. Okay, so we want to solve the differential equation y to the 1/2 dy over dx plus y to the 3/2 equals 1. So we got a couple of y's to the power here. Okay, so first thing we always want to do with the Bernoulli equation is get this into standard form. So Bernoulli equation, standard form, we can just continue this on up top. It's going to be dy over dx plus p of x times y equals q of x times y to some power. Okay, so that's our standard form. So what we need to do for this first step, so we'll say step 0. What we need to do is get our derivative naked. So get dy over dx naked. And when we do that, we need to divide both sides by that y to the 1/2. And so what we get is dy over dx plus y to the 3/2 over y to the 1/2 equals 1 y to the divided by y to the 1/2. All right, so let's clean up a couple things. Y to the 3/2 divided by y to the 1/2. Well, that works out kind of well for us, and that just becomes y. Okay. And we're going to bring up that y to the 1/2 to give us our clean looking n. And so what we get is dy over dx plus y equals y to the negative 1/2. And we want to bring up that negative 1/2 because that negative 1/2 gives us our n. N equals negative 1/2 that we have in our standard form. Okay, so we have our Bernoulli equation in standard form now. And what we want to do is start setting up for our substitution. So step 1, we want to get our u. So u equals our y to the 1 minus n. And we want to solve for y and dy over dx. Okay, so let's go ahead and try this out. So remember, we have that n equals negative 1/2, and we're going to use this to get our u. So u equals y to the 1 minus negative 1/2. Okay, be careful with the negatives. And what we get is u equals y to the 1 plus 1/2, which would be 3/2. Okay, but remember, we want to solve for y, we want to solve for dy, so we need to use some algebra and calculus to acquire these two. So let's use our algebra. We have u equals y to the 3/2. I want to solve for y, so I need to undo this power of 3/2. So what I need to do is raise both sides to the 2/3. Okay, so when I do that, it'll cancel out the power and the y. And so what I'm left with is U to the 2/3 equals just Y, but I want to rewrite this a bit. I just prefer the Y on the left-hand side. And so I have U to the 2/3. So now let's do some calculus. Let's get our derivative. Okay, so now we have Y equals, or let's just take the derivative. That's okay. So dy over dx. If I take a derivative of U to the 2/3, that would be 2/3 U to the -1/3 du over dx. Okay, and that's my derivative. So I have my y, I have my dy. We're going to move on to step two and now substitute. So step two, substitute y dy over dx into the differential equation. So my differential equation from up above is dy over dx plus y equals y to the -1/2. So I'm going to start substituting in my y and my dy. So this would be 2/3 u to the -1/3 du over dx plus y, which is u to the 2/3 equals y to the -1/2. So this would be u to the 2/3 raised to the -1/2. Okay, so a lot of fractions with power going on. So let's clean this up. Let's distribute in the power, drop some of these parentheses, and what we get is 2/3 u to the -1/3 du over dx plus u to the 2/3 equals u to the -1/3. The twos would cancel out when you distribute in that exponent. Okay, so let's rewrite this one more time. This will make it easier when we get into our linear equation time. But let's rewrite again. Let's bring this negative exponents down into the bottom. So let's rewrite it like this. 2/3 u, excuse me, 2/3 times 1 over u to the 1/3. I'm bringing down this negative exponent. Still times du over dx plus u to the 2/3. And I'm also bringing down this negative exponent. So 1 over u to the 1/3. Okay, so that takes care of our substitution and cleaning it up a bit. Let's move on to step three, where we are going to get into our linear equation time. Okay, and remember the standard form. Standard form for linear equation is dy over dx plus p of x times y equals some function of x cubed. Okay, no y to the n. That's a Bernoulli. So now we have our linear equation that we're going to get into. And so what we want to do is get du over dx naked. We want to get our differential equation that we just got into standard form for a linear equation. And the way we do that is getting our derivative naked. So let's look what we have right here. We have 2/3 times 1 over u to the 1/3 times du over dx plus u to the 2/3 equals 1 over u to the 1/3. And we want to get our derivative naked, so we're going to multiply both sides by the term that's multiplying our derivative to undo. So this is why we kind of wrote it out a little long like this, 2/3, 1 over u to the 1/3, just so it makes it easier to see the multiplication. But what we would multiply this by is 3/2 u to the 1/3. And same thing on the right hand side, 3/2 u to the 1/3. And the threes cancel out with the 3, 2, and 2, 1/3 and 1/3. And that even works out well on the right hand side as well. Okay, so that's our getting derivative naked. And so what we are left with is du over dx plus 3/2 u to the 2/3 times u to the 1/3 just ends up being u, and then 3/2 on the right hand side. So remember, we just have a power of u here, so this is good. Just first power of u. That means we're on the right track. Okay, so now we are in standard form for a linear equation. And now how do we solve a linear equation? We got to get the integrating factor and multiply to both sides. So let's keep on moving down. So integrating factor mu of x equals e to the integral of p of x dx. So 3/2 is going to be my p of x, and 3/2 is also my q of x. So same thing on the left and right side. Okay, so my integrating factor is the integral of 3/2, which is just e to the 3/2 x. So that's my integrating factor. And so we want to multiply to both sides, okay? And what we get is, let me just rewrite it, du over dx plus 3/2 u equals 3/2. Gonna multiply both sides by e to the 3/2 x, e to the 3/2 x. And what we get is e to the 3/2 x du over dx plus 3/2. I'm gonna write it like this, e to the 3/2 x times u equals 3/2 e to the 3/2 x. And so the reason I wrote it like this is because this is going to be my f, this is my g prime, this is my f prime, this is my g. Remember, it's a derivative of a product. So it's a derivative of a product, so that means what I have is a derivative of e to the 3/2 x times u. And then the right-hand side just stays the same. Remember, this is my f, and that's my g. Okay, so if I integrate this, Derivative and integral cancel out. What I'm left with is e to the 3 halves x times u equals the integral of 3 halves e to the 3 halves. So another mental u sub situation. Okay, so what you end up with is 3 halves times e to the 3 halves x over, you know, 3 halves with the mental u sub. It's just 1 over that constant inside. So what this ends up being is e to the 3 halves x times u equals 3 halves times 2/3 e to the 3 halves x. And that works out nicely. Constants cancel out. So e to the 3 halves x times u equals e to the 3 halves x. Oh, excuse me, forgot my plus c. And then I'm going to divide both sides by e to the 3 halves x to solve for u. So that cancels out. And this also cancels out too on the right-hand side. My e to 3 halves x cancel out. And so what I'm left with is u equals 1 plus c over e to the 3 halves x. Okay, so looks good now. And what we're going to do is substitute back in our y. So step 4, substitute back in y. Okay, so let's recall a bit. U equals y to the 3 halves. And so let's plug that back in. And so we get y to the 3 halves equals 1 plus c over e to the 3 halves x. So before we even solve for y, let's go ahead and use our initial condition from the very beginning of the problem. Y of 0 equals 4. We're going to use that to solve for c now, just in case it gets a little harder to solve for c. So we're going to use our initial condition, y of 0 equals 4, and we're going to plug this in now. This would be 4 to the 3 halves equals 1 plus c over e to the 3 halves times 0. And so 4 to the 3 halves, if you put that in our calculator or think about it, it'll end up being 8. Okay. 8 equals 1 plus c over e to the 3 halves times 0. Well, that's just e to the 0, which is just 1. And so c is going to equal 7. So we take this 7, plug it back into c, and so we get y to the 3 halves equals 1 plus 7 over e to the 3 halves times x. And then I want to solve for y, so, let's just raise both sides to the 2/3 because that'll undo the power of 3 halves. And so we have 1 plus 7 over, let's bring this up. Let's bring up the exponent, e to the negative 3 halves x, all raised to 2/3. And that's the answer. We solved for our constants. There's no domain or interval issues because uh, we have the exponent in the denominator, and the exponent can never be 0. So this is our answer with the initial value problem. Okay, so Once again, Bernoulli equations take a long time to solve. We're essentially solving an equation with substitution and then with the linear method, which is long in itself. So it takes a while. Make sure you take your time. Make sure you get the right indicators, such as, you're getting in your linear equation component, you're getting a derivative of a product. Okay, that's a good key. And that you are getting just a power of u to to the first power uh before you start into integrating factor and so on and so forth. So keep a lookout for those. Those just tell you're doing it correctly. But that's it for this video. A little more component with getting a constant, but hopefully you're able to follow. And thank you for watching. I'll see you in the next one. Okay, take care.